Okay, so yesterday we talked about polar coordinates and rectangular coordinates on the complex plane. I said I would do a couple of homework problems before going on to the next thing, and Diego hit me with one of the problems.
Can we do 38?
38. Now I believe you'll have to plug a calculator for this, and someone will have to tell me. Read me what it says.
Parentheses, cosine 6 plus I sin 6.
I'm going to abbreviate that cis 6. Now, the big thing to notice here is there is no degree symbol. So we're not talking about 6 degrees, which you wouldn't know without a calculator. We're talking about 6 radians. Okay? So that may have been a confusing factor for some people. 6 radians, when you talk about radians, you have to remember they're not all multiples of pi. They do exist in other multiples. Just to give you a rough idea what we're talking about, 2 pi is approximately 6.28, correct? Double 3.14? Okay? So I'm guessing, so 6 radians is something a little bit less than 2 pi, 330, 325, somewhere in that range maybe. I don't know exactly. I could find out by converting. But this is going to be somewhere in quadrant 3, I can guarantee that. So in order to do this, turn this into, the directions are to turn it back into rectangular, correct? A plus bi. Put your calculator in radian mode, and A is going to be 10 cosine 6 radians, and B is going to be 10 sine 6 radians. I do not know this off the top of my head.
10 cosine is 9.6.
Positive or negative?
Positive, but it's not cosine.
Cosine should be positive, because I said it would be in quadrant 4, right?
Yeah, that was positive.
Okay, so A is, what'd you get?
9.6.
Seems reasonable. And B is?
Negative 2.8.
Okay, so negative 2.8. So I did get something in quadrant 3. It's lower than I thought it would be. So if I had to graph this point, and I'm not going to try and draw a polar graph paper, this would be the point. I mean, it's higher than I thought, actually. You go out to 9.6 on the x-axis. You go down 2.8i, negative 2.8i, on your complex axis, and this is the point 9.6 minus 2.8i. And that is where that point sits on the complex plane. Yes, sir?
Change my calculator radians and put cosine 6, I get 0.96.
And then times 10.
Oh.
Multiplying it times the length of our radius. Okay? I'm going to stop after this one, because I think the other one someone had a question on was another radian problem. Tim, does this give you an idea on how you handle these bits of hideousness? There'd be nothing wrong with converting that to degrees first and then putting in cosine, and then leaving your calculator in degree mode and putting in cosine of whatever that is. Looks like it's 340 or so just from the way I drew it, but I really have no idea off the top of my head, except that it is in quadrant 3 because it's just a little less than 2 pi.
Did you go from the polar to regular?
Yes, that's a good idea. May I just erase this bit and do it right here? Okay, give people a little more time to look. What number?
30, for example.
Okay, and what do you have?
20 minus 21i.
20 minus 21i. Okay, again, this is another one in quadrant 4. If we were on the rectangular, well, we are on the rectangular plane right now. There's your x, there's your I. So you go over about 20 and go down a similar amount. I don't know if I'm drawing that big enough for the camera, but it is in high def. So we can freeze it and zoom it. It's almost a 45-degree angle. Almost a 45-degree angle to the x-axis, because those are almost the same amount, 20 and 21. But it's not. So now we have to find this angle.
I found the radius.
Radius is the Pythagorean Theorem, right?
Yeah.
So your radius is going to be 20 squared plus negative 21 squared, which is going to be about what?
29.
29?
Yeah.
Yeah, about times root 2, which is about 1.4. Okay, that's about right. So that's about 29. So we're going to get 29 cis. How do I find this angle?
Well, you can find the other ones, subtract from 360.
Perfect. Or we could use the negative. Your calculator can give you this angle. Remember, your calculator only gives from, you're going to use the inverse tangent, first of all. Let's go back a step. Theta equals the inverse tangent of your y over your x, so that's negative 21 over 20. And what's that get you?
Negative 0.8.
You're still in radians, huh? Nothing wrong with that. Oh, did your book have, is that what the answer to the back of the book was? Like 2 pi minus 0.8?
No, it was.
I don't want to get into that too much. That was just a little.
In degrees is negative 46 point.
Negative 46.4 degrees. Take that away from 360 for me. Or add the negative to 360. 313?
Yeah.
0.6. Okay. So our complex number is going to be 29 cis 313.6 degrees. It's not exact because it's not multiples of pi and square and perfect square roots, but that'll get you there.
Does it matter if you do it in degrees or radians? Is there one you
No. You would take, it would be about, what, 6.2 in radians, because you'd take 6, no, it wouldn't be, I'm sorry. It'd be about 5 point something. You would take 6.28, 5.47. Okay, yeah.
In the book, they said something, they did inverse tangent, but then they added pi.
Yeah, we'll,
They added pi. Yeah, so I got confused.
I think they're just trying to change quadrant. Maybe, because your calculator, remember, only gives you, I'll look at that later, but just stick with this for now. But please remember, your calculator only gives you quadrant 1 and quadrant 4 answers. Okay? But that's okay, because we knew this one was in quadrant 4, so we were good. If you know that it's in quadrant 2 or quadrant 3, you have to do a little bit of unit circle calculations to figure out what the angle is. Just know that you're only getting the reference angle. This could be here or here. A positive angle could be here or here. Take a quick look at it. Because they noticed it's in quadrant 2. So they wanted to move it 180 degrees. That's what they were doing. So if you get this negative tangents are here and here. So you could be looking at either one. We only know it's here because we know it's in quadrant 3 by the values of A and B. And rather than redo it in radians, they just added pi to move it there. That's just adding 3 degrees. Okay, good. All right, now for the new stuff. Are you ready? Somewhat. All right. This today is why I love polar coordinates. Polar coordinates are a lot like a vector. They're a magnitude and a direction. And I told you guys how the complex plane came about looking at numbers like vectors, remember? It was all a magnitude and a direction, r comma theta. We looked at how 1 comma 90 is the square root of 1 comma 180. Remember that?
Yeah.
All the rules of multiplication and exponents I showed you on that day with vectors work with polar complex numbers, and they work in the cis form. So, for example, let's say you want to multiply,
Is there a title for this? Do you know?
yes, that's a good plan. I am really out of it today, I apologize. This is multiplication, division, and exponents with polar complex numbers. Aren't you glad you asked for that long title, Diego? I can't think of a shorter way to say that, other than everything we didn't do yesterday.
Operation. Complex.
What you don't want to add and subtract with polar complex. You want to add and subtract with rectangular, and I'll show you why in a second. It goes back to how vectors work, which by the time I'll try to make that connection. All right, if you want to, quick example in rectangular form. If I want to multiply 1 plus root 3I times root 2 plus root 2I. By the way, did I give any Easter eggs away in what, did I give any hints away in what polar form I'm talking about, what angles I'm dealing with?
That one, yeah, that was 45.
That was 45.
The other one's
That was 30.
30.
Is it 30? It's either 30 or 60.
Why?
We'll find out. There's a 30, 60, 90 triangle here, and there's a 45, 45, 90 triangle here. And both radiuses, both hypotenuses are 1. Let's multiply this. To multiply this, we FOIL, right? I'm going to get square root of 2 first, plus root 2I plus root 6I plus root 6I squared. Correct? I squared is -1, so my real component is going to be root 2 minus root 6, and my non-real component is going to be root 2 plus root 6I. How satisfying was that? Not particularly.
Great.
In this case, this point here, 1 plus root 3I, I'm talking about going over 1 and up root 3. So I'm looking at a hypotenuse of 2, I think I just missaid that a moment ago, and a 60-degree angle. So this point, here's my next example. Now I'm going to multiply 2 cis 60 degrees, which is this number, and this one is 1 cis 45 degrees. Now the whole point to my little lecture on where the complex plane comes from was that when you're on the complex plane, when you deal with numbers just in terms of direction and magnitude, you're basically dealing with vectors. And that there's a very straightforward way to multiply vectors. Not the dot product, not the cross product. And that straightforward way was you multiply the magnitudes, but you add the angles. You multiply the magnitudes, but you add the angles. The magnitudes, what's 2 times 1?
2.
The angles, what is 60 plus 45? Boom, I'm done. Which was easier? Polar, definitely, people are pointing. Yeah, it's much easier to multiply and divide and deal with powers, exponents, and roots in polar form with complex numbers than it is in this form.
What we learned, what we learned to do it that way.
Because adding and subtracting in this way is insane.
Oh,
I mean, well, how did we add and subtract vectors? We found the components of the vectors, right? If I gave you a vector, if I gave you the magnitude and direction, you quickly changed it to that to add the vector form, right? What is the component form of 2 cis 60? It has a horizontal component of 1 and a vertical component of root 3. What is the component form of 1 cis 45? It has a vertical component, a horizontal component of root 2 and a vertical component of root 2. So in order to add those polar numbers, you'd have to change them back to this anyway. Plus, this lets us talk about complex roots of quadratics before you guys have learned the unit circle. So there's a couple reasons. They're both useful for different things. But oh my god, if you're multiplying, dividing, or dealing with powers, you so want to be in polar form. It's so much easier, it's more fun. Let's see, check this out with the division. Are you ready?
Division is not really division, it's just a bunch out there.
Division is different now with this. With division, give me a second to make one up that will actually work. So if I do 5 root 3 plus 5I, bless you, over, put this one in another quadrant now. And I got to keep it to like 30s, 60s, 90s, and 45s. So, no, I don't. Actually, I'm just going to do this. I'm going to do another example. And I'm just going to do this divided by negative 4i. Divided by negative 4i. How would you do this the old way? We didn't really go over how to divide things. You got a couple more options here. One of them, based on what I said before, is you would multiply top and bottom by something to get rid of that I. What would get rid of that I? Another I. I could do positive 4i, or in this case, because I don't have a binomial on the bottom, what would happen if I just multiplied by I over I? Yeah. So what I'm going to get now is 5 root 3i plus 5i squared, over negative 4i squared. And everywhere I see an I squared, what can I change it to? Negative 1. Awesome. So 5 times negative 1, I'm going to make that a negative 5 over here. I am going to put the plus 5 root 3 afterwards. What's 4 times negative 1? Negative 4 times negative 1? 4. So my final form of this is going to be negative 5/4 plus 5 root 3 over 4i. And that was a relatively simple one, right? That was a relatively simple bit of division between complex numbers in rectangular form. So I didn't put a binomial on the bottom. Let's look at this as polar complex numbers now. 5 root 3 plus 5i. Can you guys change that to polar form? Maybe. Let's draw the triangle. If I go 5 root 3 out on the x-axis, and then I go up 5 units, what kind of triangle is that? 30, 60, 90. What's this angle? What's the hypotenuse? 10. So I'm looking here at 10 cis 30. Negative 4i. By this scale, that would be down here somewhere. How do I represent that with cis? You're on the right track. You're thinking right. What angle is that? It's 270. And how far is it from the origin? How far is it from the origin? Half, right? How far is, if I just ask how far is something from the origin, do I care about positive or negative?
I'm not sure.
This is, remember what we did with polar coordinates. This is not negative. This is 4 cis 270. Okay? Polar division. In this case, you divide the magnitudes.
Like actually divide them, or
Like actually divide them. And you subtract the angles. So this equals, what's 10 divided by 4?
2.5.
Yeah, I'm just going to say 5 halves. It's a little easier for me. What's 30 minus 270? Negative 240. Switch that around to a standard angle. Negative 240 is the same as positive. Positive 120. Diego. That mental math under pressure.
Here, where's that chart of yours?
Now this is a crazy kind of thought. It's very hard to think of this intuitively, but remember, bless you, we started with this point up here. This is 10 cis 30 degrees, right? This is negative 4i, also known as 4 cis 270. If I divide 10 cis 30 by 4 cis 270, the point I get is only 2.5 units away from the origin at a 120-degree angle. You get a point up here. That number, 5 cis 120, I go to 120 degrees, and it's 2.5 units away from the origin there. So this number in the complex plane divided by this number puts me here. Vectors are weird, and so are complex numbers. So there's no real good intuitive way to do this.
You just have to know it.
You have to know this way. Yeah, it's not going to be like you can picture. We're not going to be taking a pizza and cutting it into 4 slices to figure out what 1/4 of the pizza is.
Do that.
This division's a little harder. Did you have a question, Nate?
I'm hungry.
All right, that's almost lunch. Any questions on multiplication and division? Okay, multiply the amounts. I'll review the rules in general at the end. I'll pause on that part. Now for my next example. Exponents. I don't know if you guys remember how we handled exponents when I first introduced this idea of using direction instead of negative. But with direction, with an exponent, if you have, for example, 5 cis, I'm just going to say 30 degrees cubed. 5 cis 30 degrees cubed.
You're thinking of multiplying them?
Well, it's. Remember I said on that first day, I said everything goes up a notch on the order of operations. So what you do is, the 5 does get raised to the power. The 5 does get the exponent. But the 30 doesn't get raised to the 3rd power. We were adding the angles. What's the next thing up from addition on the order of operations? Multiplications. We multiply this times 30. So 5 cis 30, 30 degrees up in quadrant 1 on the complex plane, 5 units from the origin, becomes 125 cis 90 when you cube it.
That's it.
Yeah.
That's a lot.
Now 5 cis 30 isn't bad. If we were to do this in rectangular form, 5 cis 30, let's see, 30 degrees, so the cosine of 30 is root 3 over 2, right? So that's 5 root 3 over 2, and the sine of 30 is 30 degrees, is 1/2, sorry, so that's 1/2, plus 5 I cubed. To do that in rectangular form, you would have to FOIL this, and then you would have to multiply that trinomial by 5 root 3 over 2 plus 5 I again. So do you think that would be a lot of fun to do? Now, it's so much easier to just go, oh, it's 5 cubed and 3 times 30. Which, incidentally, this answer in rectangular form, can anyone tell me what this answer is in rectangular form just by looking at it?
So
90 degrees, it's on the I-axis.
are we 125
125.
plus
Oh no, you've already gone in the wrong direction. If you're up on the 90-degree axis, you're up on, here's your x-axis, here's your y-axis. If you're up here, do you have any x components? No, so you have no real components at all. All you are is up on the positive axis. So this becomes 125 cis 90. That's just 125i. There's no, it's just the bi part, there's no a. It's not on the real number line at all. Bless you. You can also write it as 0 plus 125i. You would not want to do this. This wouldn't be fun. This is easy. Especially if we raise it to the 5th, 6th, 7th, 8th power. One that's fair to do without a calculator is if I keep the base low. Like another example would be, what is 2 cis 135 to the 5th power? That's annoying without a calculator, but I don't think it's completely unfair. First, the process. Raise 2 to the 5th power and multiply 5 times your angle. Anyone know what 2 to the 5th is off the top of their head?
32.
32. Very good. Danny, you knew that, right?
Yep.
All right. What's 5 times 135? It's 500 plus 150
675.
plus 25. Yep, 675. Should we leave that as 675?
No.
No.
Yeah.
No.
Yeah, you'd like that plan? What's 675 minus 360? Let's get this back in. Yeah. So that's where I would graph that point. For some math, by the way, it might make a difference. This is where I would graph it. So saying equal is a little tricky. I would graph it here. But you remember how I said the square root of 4 on that day where we looked where the complex plane came from? It sort of depended whether you started at 0 or 360. There's a bit of craziness there. For certain operations on the complex plane, these may not be the same. You may not get the same answers. So if you had another step after this, you would want to use the 675. But if you had to graph it, you would put it here. Does that make sense? These are in the same spot, but now you can't always just interchange these. And I'll show you an example of where that might be problematic in 1 sec. May I erase this example?
Great.
Okay. Tell me when. Everyone else, take your time, contemplate this. This
Wait, do
connects.
we need the part at the bottom of 5 or 3 or 2 or?
If it helps you remember it, if it helps you appreciate why you don't want to do it this way, especially if.
I'm just going to confuse myself.
All right. Let me mention that real quick here. 2 cis 135. That would be in rectangular form root 2 negative root 2 plus root 2I. Would you want to expand this 5 times and do all that FOIL
No.
just to get 32 cis 315?
Is there a cis button on the calculator?
I don't think so.
But,
Oh, if you go into polar mode, maybe.
but does,
There is a polar mode.
Yeah, there's a polar mode. I'm honestly not sure because we
Doesn't-
usually stick to non-calculator.
it doesn't give you an operation,
Yeah, I'm not sure how that would work in the calculator.
I'm actually in polar. So.
Your calculator does, you can put your calculator in a non-real mode and it'll give you rectangular answers. But I don't think it'll give you, we'll try that in a sec. But for now, here is the trickiest part. And you guys are about to learn my favorite theorem in math. I have a favorite theorem. And I already showed you the beginning of it. De Moivre's theorem. I love this one. It's kind of elegant. What's the cube root of 8? 2. What is 8 on the polar complex plane? How would I write that? How do I write 8 as a polar complex number? Robbie's demonstrating where I graph it. I'd go, I'm going to draw this bigger, this gets important. To graph this, I would go 8 units out on the x-axis, right? Plus what? What i's do I add to this? Plus 0i. Robbie was looking at me like I was nuts when I asked that. But you see how I can write it as 8 plus 0i? Every number can be written this way, if you want. That's in rectangular form. What's 8 in polar form? Polar rectangular form. Polar complex form, excuse me.
Are equals,
What angle is that?
0, 4, 3, 6, 7.
Let's call it 8 cis 0 for now. Okay? Roots work exactly like exponents with one exception in the complex plane. If I do 8 cis 0, to the 1/3 power. Is this the same question as this? Okay. Then I'll get 8 to the 1/3 cis 1/3 times 0, which is, and 8 to the 1/3 we said is 2. So I get 2 cis 0, which is 2 at 0 degrees. So we're all good, right? Here's what de Moivre's theorem says. This is only the principal root. That's just the principal root. You have more. And what de Moivre's theorem says is if you're finding a cube root, the cube root of any number produces 3 roots evenly spaced on a circle. Now, I didn't just make this theorem about cube roots. 4th roots will get you 4 roots evenly spaced. In fact, I'm going to generalize this. The nth root of any number will get you n roots evenly spaced on a circle. Now we're finding a cube root. Divide 360 degrees by 3, what do you get? 360 divided by 3, you get 120. So the cube root of 8, if you're just on a number line, is 2. Cube root of 8 on the complex plane, according to de Moivre, has a principal root at 2. And then we draw a circle. And there's another root 120 degrees away from that, up here at 2 cis 120. And there's another root 120 degrees away from that, at 2 cis 240. And those are the 3 roots of the 3 cube roots of 8. It's really elegant. It kind of makes sense that they should be there. I'm not sure why that's always made intuitive sense to me, when so many other things I feel like I have to think about. But and he proved it's true for any number on this plane, which means any number on the x-axis this is true of as well. Oddly enough, you've already learned some of this. You just didn't really know it. May I erase this part?
Yeah.
I'll do another example. What's the square root of 4? 4?
Negative 2.
2 or negative 2. Thank you, Danny. Square root of 4 is plus or minus 2, you guys have learned, right? Okay, let's do this a different way. What is 2 cis 0 degrees? Sorry, what's 4 cis 0 degrees to the 1/2 power?
It's the square root of it?
Yes, it is a square root. That's what the 1/2 means, but that wasn't the important part of the question. So we follow our rule for exponents, which is you take the length raised to that power, and you multiply the angle by that exponent, which should be 1/2. I'm writing the wrong number down the first time, every time here. So as my principal root, I get 2 cis 0 degrees. This agrees with what Diego first said. The square root of 4 is 2. The square root of 4 cis 0 is 2 cis 0. But de Moivre's theorem says, if you're looking at a square root, you have 2 roots evenly spaced. If my first root is here, and I got to put the other one on a circle evenly spaced, where's it going to be?
Negative 2.
Negative 2, 0 on the rectangular number line, perfect. Or, in this system, it's going to be 2 cis 180 degrees, which is the same thing as negative 2. Remember last week when I said this could be 2, 0 or 2, 180? Polar complex numbers are that exact system I introduced to you last week. They're exactly what I said. This is where the imaginary plane comes from. And all the rules I said, you know, that we didn't use for negative numbers, we use them here. De Moivre's theorem is what tells us the square root of 4 is plus or minus 2, as we're used to it. I want to do another example of this with a graph. And I'll just graph the answers.
We have time.
Barely yet. Just one more. So this example is 625 cis 75 degrees. 625 cis 75 degrees. What's the fifth root and the four other roots? Well, let's see. 625, I'm sorry, the fourth root. I meant to do fourth root and 60 degrees. And then you're on the right track. You knew what I was going for. Not really writing anything down the right way first try there. 625 to the
Maybe
1/4.
you should just stop teaching us Spanish.
I think that's it.
You're writing everything higher, maybe you should get our grades in like
625 to the 1/4 cis, 1/4 times 60. Robbie, what did you say 625 to the 1/4 was? 5. 5 cubed is 125. Multiply 125 times 5 again, you'll get 625. What is 1/4 times 60? 15. That's my principal root. How many other roots am I looking for? 3 more. 4 total. What is 360 degrees divided by 4?
90?
Yeah, 36 divided by 4, that's 90 degrees. So my other answers are 5 cis, add 90 to that, 105. Double check me. Making silly mistakes today. 5 cis 195 and 5 cis 285. And then if I add another 90 to this, I get 375, which would take me right back to there. So those are my 4 roots, evenly spaced on the circle.
Get you got this.
Some you do. And I don't want you to get confused by one other thing. I'm going to won't have time to graph it, but I do want to mention complex numbers are often given in the form z equals a plus bi, or z equals r cis theta. So sometime in your homework tonight, they might give you z like this, like z sub 1 and z sub 2, and they might ask you to find z1 over z2. That just means divide the two numbers, or z2 plus z1. I've stayed away from the z notation because I wanted to get the idea down. But if you see that in the homework, don't flip out. Z is just a shortcut for writing the whole complex number. I'm not sure how that became commonly accepted. Any questions on De Moivre's theorem or how you would graph this real quick?
I mean, you just graph like a regular polar one, right?
Yep. If you're on a polar graph, it's easy. You go 5 out to 15 degrees, and you go out to about, when you're done, they should all be 90 degrees apart. And they should all, if you have your polar graph paper, they should all be on that 5th circle out to show your 5 from the origin. It should look something like that.
Yeah, so you just graph like a regular.
Yeah. But I always liked De Moivre's theorem. It's a fun one. Can you imagine trying to figure this out with rectangular?
No.
I wouldn't.
I can imagine just not doing it.
I can imagine giving up. All right, your homework tonight is up here, but it's not online yet. And it is, my God, it's a lot to write. Page, not that much to do. Page 596, 10 through 20, even. Page 605, I think it said. Page 605, 6, 8, no short-term memory anymore, 12 through 24 even. And I'm changing the directions a little bit. It says put your answers in rectangular form, and I don't care. Leave them in polar form, that's fine. And if it says just find the principal root, I want you to find all the roots. You guys understand those two differences in the homework? So do it the way I did it up here. We'll talk about the differences yesterday. Tomorrow, show you one more quick thing, review tomorrow and Friday, and test Friday. See you tomorrow and Thursday.